My name is Varshit, and now we are going to discuss the topic deadlock detection and avoidance for shared logical resources. Much research has focused on the deadlock problem in computer systems. However, most of this work relates to resources that must be exclusively accessed recent work in operating systems and database management systems. It indicates that each condition may be too strong when the sharing of information itself is considered. Our paper examines the deadlock problem using an abstract model that permits resource sharing. This sharing enables increased concurrently while enforcing consistency constraints within and among units of information. A deadlock detection method is presented and a deadlock avoidance strategy for pre-clamped systems is discussed. First of all, deadlock is a place where two resources have been using for one process and the other process is waiting for a resource. It's like a traffic jam, and the proposed method for relaxing the exclusive use requirements permits process to access data in different ways, some of which may execute concurrently with others. This increases throughput in systems where locking for consistency causes underutilization of physical resources. An improvement in response time may also result from reduced blocking. Before considering deadlock issues, we examine the concept of sharing. In particular, we define the manner in which processes may concurrently access resources. A logical resource is a named, seriously reusable entity which may be concurrently accessed. Concurrently, restrictions depend upon this manner in which processes may access a resource. Logical resources differ from physical resources. In the logical resources have only one conceptual unit, and in this paper resources refers to a logical resource. A mode is a set of permitted uses of a resource, and thus application dependent. Modes are used to permit sharing while enforcing consistency and synchronization constraints. Modes A and B are compatible. If any resource being accessed in mode A, and it can simultaneously be accessed in mode B, otherwise they are incompatible. In the SE system, S mode is compatible with itself, but not with E mode. The compatibility relation is not usually reflexive as E mode is compatible with itself, and whereas compatibility in model system is normally symmetric since the order of first access is not significant. The acquisition and use of a resource is characterized as follows. A process must request the needed resource by giving the names and model of use to the resource manager. The process then waits or it's blocked until the requested resource are available in compatible modes. When a resource is available, the resource manager may allocate or grant the request, and the process may use the resource in any manner permitted by the mode. When finished with the resource, the process releases the resource. Here we can see A is an processor and which sends a request for B to share a resource, and B is sending the information for process 2, and process 2 is sending a request for logical resource A. This is the situation where deadlock occurs. A block process is deadlocked if no legal sequence of allocations and releases by unblocked process will allow the process to become unblocked. A system contains a deadlock. If any process is deadlocked, a graph representing the state of all active process and resources in a system is called the system resource allocation graph. Directed bipartite graphs will labeled edges are used to represent process, resources, and their interactions. Square nodes significantly process and round nodes deficit resources. A resource is represented by a request edge, directed from the node of requesting process to the node. An assignment edge directed from a resource node to process node indicates that the process has been granted by the resource. Each edge is labeled by the mode of corresponding request or allocation. Granting a request transforms the request edge into an assignment edge. A release deletes the corresponding assignment's edge, and it is a directed path in which each request edge is followed by an assignment edge labeled by an incompatible mode. Well, deadlock detection is a method for finding deadlock after it has occurred. In this section, deadlock detection for the logical resource model will be examined. Proofs of all theorems are contained in the appendix, where theorem 1, a system state represented by a resource allocation graph, contains a deadlock if and only if graph contains a D cycle. All processes in the D cycle are deadlocked. Theorem proves a simple method for detecting deadlock. The complexity of an algorithm implementing this is on the order of number of edges in the graph. This algorithm can be performed so long as the allocation graph represents the current state of the system, and this state does not change during execution of the cycle detection algorithm. Often, a resource manager immediately grants every request compatible with the current allocations, and such a system called expedient. It's not always optimal. If a process requests to resources but not only is available, the resource manager may tie up the available resource unnecessarily. This may lead to deadlock, that is, avoidance if the resources were assigned only after both were available. Assume the compatibility relations for all modes in a system are symmetric and transitive, and that the resource manager is expedient. Then the system state represented by a resource allocation graph contains a deadlock if and only the graph contains a cycle, and if the algorithm is invoked each time a request is blocked, the average complexity will be much less than the maximum complexity, since only those links connected to the blocking resource. And due to the possibility of sharing, the algorithm must be slightly more complex than the equivalent one or more non shareable single unit resources. This cycle detection algorithm is simpler than the theorem one, but the order of complexity is the same. Deadlock avoidance. Giving the resource manager advanced information may enable it to better schedule resources. A process may claim a resource for a given node before requesting it and delete the claim when the process no longer requires the resources claim, and detection of claims never cause a process. In a resource allocation graph, a claim edge indicates the possible future request for a resource. It resembles a request edge in the direction, but it is represented by a dashed line. Since processors may wish to have multiple inconvertible claims for a resource, claim links are not converted to request link as all claim system. If, however, there is at most one claim link from any process to any resource, no information is lost by converting claim links to request link when a request is made for the claimed mode. Released assignments links revert to claim links if they had originally been claim links. We can see in that diagram. Well, one process has a send a request for A, and again it sends the request for A, and it sends for request for B also, and the process 2 sends the request for resource A and resource B. It is the perfect example of a claim system resource allocation graph. And we can see figure 5, process not allowed to begin execution concurrently under the all at once strategy. Here one process sharing one resource only, and the only process is sending the request for two resources. In claim systems, an allocation strategy temporarily prevents allocation, which might lead to deadlock. A process which is not blocked but it's not granted a request because of the allocation strategy is called allocation blocked, and the request by process 1 for resource is a blocked. A possible deadlock path or PD path is a path in which all claims and request links in the path are followed by incompatibility label assignments links, and a claim system in which all claims are safe is said to be safely claimed. And this particular strategy called a strategy is the only considered in this paper. A claim is a safe if it does not violate the A strategy at the time it is made. And when an S allocation is first in the queue, as well as incoming S request when an S allocation is being served, indicates higher resource utilization as well as lower mean and standard deviation for waiting time in a wide variety of arrival and service distributions. And a safely claimed system is guaranteed deadlock free if and only if a strategy is followed. Theorem 2 provides a method for avoiding deadlock when claims are known. Check each request and do not allocate if it is allocation would complete a PD circle. Since only that part of the graph connected to the resources, the average complexity should be much smaller than the order of number of edges. A similar algorithm that places arriving as request at the end of the queue when an e request is in the queue showed better results only in case when there was a low coefficient of variation in the arrival or service distribution. By viewing the bipartite direct graph representation of all claims as an underrated graph, theorem to suggest a deadlock prevention methods to similar all at once location. This strategy avoids deadlock when scheduling the initialization of process rather than checking time a process requests a resource. Allocation and request edges are possible only between process resource node pairs. When it claim exists, thank you.